In this episode, we're going to be solving a little different problem compared to the ones that we solved before. We just have two capacitors in series with each other. Oh, that's nice. It's an innocent looking problem. But the question is, we need to find out the maximum charge that these capacitors can hold at electrostatic equilibrium such that neither of them undergo breakdown. What is this whole breakdown business? Well, what's given over here are what is called as the breakdown voltage. This just tells us the maximum voltage that we can put across this capacitor, after which the capacitor will get damaged. Sparking is going to take place. So that means this guy is not supposed to get a voltage more than 10 volts, and similarly this guy is not supposed to get a voltage more than 20 volts. So under that circumstances, the question is, what is the maximum charge that these guys can have? Because obviously once the charge exceeds a particular point, the voltage across either one of them might exceed, or even both of them might exceed that given voltage, that given breakdown voltage, and then the whole thing can break. So that's the question. Okay, so how do we do this? Well, the first thing to understand is the following, that these guys are in series with each other and therefore they're supposed to have the same charge. That's one. And if the charge on the capacitor is the maximum, I mean, think of them as one big equivalent capacitor. If the charge on that capacitor is supposed to be maximum, then the voltage across the capacitor is supposed to be maximum. Because remember, Q is just C is equal to, Q max would be just C times V max. So we just have to figure out what is the maximum voltage. So we need to calculate the maximum voltage between A and B such that no capacitors undergo breakdown. That's our question. Now at first, I'm just going to tell you what my intuition would be if I don't think about this too much. At first we would say, well, since I want the maximum voltage over here, that's very simple. All we have to do is, let's zoom that over here. All we have to do is make sure that this guy gets 10 volts. This guy gets 10 volts because that's the maximum voltage that capacitor can handle. And then we have to make sure this guy gets 20 volts because that's the maximum this guy can handle. And that means the maximum voltage that these guys can handle together would be 30 volts from here to here. And once we know that, we can calculate the charge, right? No, wrong. That's not going to work out. And here's why that's not going to work out. Because the moment you put 10 volts, I don't know how you're going to do that, but let's say you put 10 volts across this guy is going to end up with a charge of, say, 5 times 10, 50 microcoulombs, okay? So this is going to be 50 microcoulombs. And this guy is going to end up with 20 times 10, 200 microcoulombs. What's the problem? Look, these guys are in series with each other and they don't have the same charge. If they don't have the same charge, this is not going to be in electrostatic equilibrium. So imagine this is positive and this is negative. So this would be positive and negative, and this would be positive and negative. And this will not be in electrostatic equilibrium. Charges will start moving from here to here because they want to equalize the charge, and boom, this capacitor is gone now. And you see, therefore, this is not the right way to do it. That's not the right answer. So let's just delete this whole mess. This is wrong. What we will do is, to find out what the maximum voltage is, let's put 5 volts over here. Let's put that, not 5 volts. Let's put that 10 volts over here, and let's find out how much voltage comes across this capacitor. If that voltage is less than 20 volt, then that's it. That's going to be the maximum voltage, because if you increase that voltage even by a single volt, then this capacitor will undergo breakdown. Then what we will do is we'll put a 20 volt here and check what's the maximum voltage over here. Well, if it turns out to be less than 10, then that will be the maximum voltage. We'll just compare the two situations, okay? So let's begin. So I'm just going to copy this first. Alright, so in situation 1, what we are going to do in situation 1, so this is case A, okay? So this is like a trial solution, so case A, and I don't think there's any other way around it. We just have to do a trial solution. Let's try to put a voltage of 10 volt over here, and let's try and calculate what's going to be the voltage at this point. Well, if the voltage over here is 10 volt, then the charge over here is going to be, so I'm going to call that charge as Q1, and that's going to be 50 microfarad, sorry, 50 microcoulomb. But since the two capacitors are in series with each other, I should have put the charge in some different color. So shoot, let's see, I'm going to put charge in this turquoise. I'm going to use this color. All right, so let's put charge Q1. That's going to be 50 microcoulomb. Okay, that will be over here. But the same charge should be over here in electrostatic equilibrium. So we know charge Q2 is also going to be 50 microcoulomb. So that is something we know. And since we now know what the charge over here is, we know that this guy is going to get 50 microcoulomb. We can calculate what the voltage that fellow will end up with. Well, the voltage that this guy will end up with is just going to be 50 micro divided by the capacitance, because V is equal to Q by C, 10 micro, and that's going to be 5 volts. So this guy is going to end up with 5 volts over here, and so the total voltage is going to be 15 volt, and that's good to go. This is a good solution because neither of the capacitors are undergoing breakdown. But we don't know whether this is the maximum yet. So let's go to case B and let's see what's going to happen. So in case B, what we are going to do is we're going to put 20 volts across this capacitor, and let's see what will be the voltage over here, just in case, just to find out what's going to happen. So in this case, we know Q2 is going to be 20 times 10. That's going to be 200 microcoulomb. If you have followed me, I'm pretty sure you know what's going to happen over here. So because of electrostatic equilibrium, charges must be same. Q1 is going to undergo 200, also going to become 200 microcoulombs. And if Q1, if this guy has 200 microcoulombs, then we can calculate what the voltage is going to be. V1 is just going to be Q divided by C, and that's going to be 40 volts. And that's a big no-no because that's going to destroy this capacitor. And so we know that this is the maximum case that can ever happen. I mean, you may ask, how do you know this is maximum? I mean, maybe something else happens. No, nothing else can happen, because the moment you increase the voltage beyond 15 volts, suppose you were to put the total voltage from here to here as, say, 16 volts, then the voltage will again get divided in the same ratio. Try and understand this. The ratio of the voltage over here is 1:2. Can you see that? This is, sorry, it's 2:1. I'm going to write that over here. The voltage over here, okay, I'm going to write that. The voltage ratio will always be 2:1. So this is going to be 2x, and this is going to be x. And if you ask me the reason for that, well, that's because the charge has to be the same. See, charge is given as C times V. If the charge on both of them has to be the same, then the voltage should have the inverse ratio as the capacitance, because the product must remain the same. Are you getting me? Therefore, notice that this capacitance is half of this capacitance, and therefore the voltage across this capacitance must be twice that of the voltage across this capacitance. So it doesn't matter what voltage you put. What's going to happen is, if you were to put 15 volts, as you can see, we worked out, you're going to get 10 here and 5 over here, and everything is going to be nice. But if you were to put anything more than 15, not only will the voltage increase here, but the voltage will also increase here. Remember, the ratio has to be always 2:1, and this capacitor is going to blow up. So we know that the maximum voltage that can come across A and B has to be 15 volts, and that translates to a maximum charge of 50 microcoulomb. So I hope I was able to give you some idea behind what goes on over here. So the answer is maximum charge, Q max, is just 50 microcoulomb. Alright, see you next time.